All right, so let's talk about data types and data structures. So within R, we're going to be working with different types of data, right? And this is not just within R, but basically when we do analysis on information that organizations collect, we have a variety of types of data. We have numeric data, which includes decimals. These are numeric values that have decimal values to them. These are also referred to as floating point values, lots of times within the computer science world. We also work with integers, and integers are just simply numbers without any kind of decimal values. We have logical values represented as like true or false, so these are booleans. And we have characters, and characters are usually identified as basically strings that are encapsulated within quotes. Now, we have a variety of data types, and we hold these different data types in certain structures within a programming language. And within R, the four main ones that we will be working with are vectors, which are one-dimensional and contain homogeneous type of data. We have matrices that are two-dimensional, so it's basically a vector that's got an extra dimension to it. We have data frames, and data frames are synonymous to kind of like an Excel spreadsheet where you can hold multiple different types of data within columns. And then we have a list, and lists are really flexible. You can hold all different types of data and even other data structures within a list. So it's like the most flexible data structure possible. All right, there are even more, both more types of data. For example, there are date strings, date timestamps that we can work with, and we'll even see how to work with those throughout this course. There's even ones that are factors. We call them factors. It's kind of a unique character data type. And then even we have other data structures such as arrays. But the ones you see on here are the primary ones we're going to be operating with throughout this course. Okay, so when we create a certain object or data value object within R, right, we can have just a numeric data type. We can have a character string that is encapsulated by quotes. We can have a logical. Now, logical ones, true or false, they need to be in all caps. So if we look over here, if I say logi equals true, but not in all caps, what's going to happen is I'm going to get an error, and it says object true is not found, and that's because true, as in all caps true, is actually an existing object within R that represents truth, right? And you can also have false, so you can have either true or false. Okay, so we can have our data value. Now we can always figure out what class a data value is by using the class function, right? So if we were to apply class to our numeric data value, we get numeric in return. If we apply class to our character string, we get character in return, and so on, right? So class kind of tells us what type of data is. Now we can even be more specific, and we can say, is a certain object a particular data type, right? So we could say is dot numeric. So we're specifically saying, is this data object a numeric object? Is this data object a character? In this case, num is a numeric value, but it is not a character, so we get false in return. And we can do that for all the different types of data. Is numeric, is character, is logical, and so on. Now we also have a class of functions that are as dot and then as dot numeric, as dot character. And these are functions that can actually change the data type to a different data type. All right, so we call this coercion. Now there are certain rules that apply with coercion. For example, values are converted to the simplest type required to represent all information. That's a little bit tough to grasp at first, but just realize that like character strings are probably the simplest data type, right? We can actually convert a number into a character string. We can convert a logical data type to a character, but we can't always convert a character to a numeric data type, right? So roughly the ordering is logical is less flexible than integer, which is less flexible than numeric, which is less flexible than character, right? So we can't necessarily always turn an integer into a logical data type. We can't turn all character data types into integers. Now, logical values have a pretty cool characteristic to them, is that they can be converted to ones and zeros, okay? And why is this important? Well, because we will see later on that if we were to get let's say a vector of true and falses, and we want to understand how many trues are in there, we can simply apply sum to that vector, right? So I can always have this Boolean string, and let's just say I'm going to add some more. True, true, false, false, right? And now I just want to know how many trues are in there. Well, I can just do bool sum of my data type, or my data vector here, and it's going to sum up all the trues in there. So I can see I have 4 trues, right? Because trues just get converted to 1 where falses are 0. And we will see many instances that we can use this in data analysis down the road. All right, so what I want you to do is go ahead and pause this video, and I want you to go through this your turn. We're going to take a look at a built-in object, pi. I want you to identify the class of it. I want you to try to coerce this object to a character, and then coerce it to a logical. So work through 1 through 4 here, and we'll pick back up in a second. All right, so hopefully you got through this. So we can see that there's an object within R. It's built in, and it's pi. It represents pi, and we can even see question mark pi, and it's going to give us a lot of these built-in data objects, such as the alphabet, which is letters, the months, and so on. But we have pi right here, the ratio of the circumference of a circle to its diameter. All right, so by default, pi is numeric, right? It is a floating point numeric value, right? So we can see that if we apply class to pi. Now, if we coerce it to a character, we see that we get the full, well, not the full, but decimal values to a very large placement level, but it just wraps that in quotes, right? So that's how it converts it to a character. So it's now no longer numeric, it's a character string. Now, we can convert the pi to a logical, but what it does, this is kind of unique, it just converts it to true, and that's because the value is not 0, right? So if you were to try to coerce any kind of numeric or number to a like a Boolean, either true or false, as long as that number is not 0, it's going to be true. If it is 0, it'll be false. And then lastly, if you do as integer, so if we coerce pi to an integer, it will just chop off all the decimal values, and it'll just be the number 3. All right, so now let's talk about some data structures. There's primarily 5 data structures in R. You have vectors, matrices, arrays, data frames, and lists. Now we spent, the previous module, we spent some good time on vectors, so we have a fairly good understanding of those. And we really don't use arrays all that much at all. So we're not going to cover those. So the ones I want to talk about here are matrices, data frames, and lists. All right, so matrices. The way to think about a matrix is it is basically a vector that now has 2 dimensions. So recall that a vector can only contain one data type, so it requires homogeneous data, and that it only has 1 dimension, okay? Well, a matrix also can only contain 1 data type. However, it has 2 dimensions. It has rows and columns, right? So here's an illustration. Both we have a numeric matrix right here, and we can also have our values of a matrix be character strings, right? So we can have all the different types of data types as within a matrix, but all the values within a matrix must be of the same data type. All right, and also all the rows and columns must be of equal length. All right, so when do we use a matrix? Well, honestly, not that often. If you need to do some matrix algebra, you can definitely do that. But for the most part, the only time I ever use matrices within R is when the output of some function is a matrix in itself. For example, you may do a correlation, right? And we'll talk more about correlation later on in the course. But if you do a correlation of a data set, you'll get the output as a matrix, right? So you may want to understand how do you extract certain parts of this matrix. If you do want to do matrix algebra, there are built-in calculations that are designed specifically for matrices. For example, here, if you want to do matrix multiplication of two matrices, we would do that with that syntax. All right, so if you are provided some output as a matrix, like how do we actually extract some stuff out of it? Or how do we do indexing with it? Well, it follows a very similar syntax to vectors where we use the bracket notation. And in fact, every single data type we work with, we can do indexing with bracket notation. However, the main thing that changes here is since we have two dimensions in a matrix, within our brackets, we need to define both the row and the column of the item we're trying to extract. Right? So say we are given this matrix here, and I can just produce this in my R session. And here's our matrix, right? So we've got 5 columns, 3 rows. If I want to get the first element in the third column, I just use bracket notation, but I need to specify which row, which is the first row, and which column, the third column. And I can get number 7 here, right? So that would be the first row and the third column, number 7. Now, you're not limited on only pulling out one element, right? We could actually say, hey, look, I want to get the first 2 rows of my matrix, but all the columns, right? So now what I can do is I specify 1 through 2 in my bracket notation for the rows, but I just leave the columns part blank. When I leave it blank, it basically is telling R, I want all of those columns, right? So now I get the first 2 rows and all columns. Or I could flip that and I could say I want to get all the rows, so I leave the rows blank, but I want to get the first 2 columns. Now, there are operators that will work across an entire matrix. And in fact, a lot of the standard functions that compute some summary statistics, such as the mean, standard deviation, variance, and so on, they will actually compute the mean, the standard deviation, the variance across all the values in that matrix, right? So here, if I apply mean to my matrix M1 that I created earlier, I see across all my elements, the average value is 6.2. Now, since we have 2 dimensions, sometimes you want to get certain computations across each column or each row. And there are a few functions built in that allow us to do that. For example, we can call the mean, there's a call means function. What that's going to do is it says compute the mean across each column, right? So now in this M1 vector that I had created apparently earlier, right here, let me snag this code. Oh, looks like I need to do all that code. There we go. All right, so now I have M1. And if I wanted to get the mean of each column within this vector, right? So that's where call means allows me to do that. Or I could get call sums across that. There's also row sum. So if I want to get the sum across sum of all the values in each row, I can do that as well. All right, so I want you to pause the video and go ahead and work through this your turn, which is gonna deal with a built-in VA, it's called VA deaths matrix. All right, so hopefully you got through this. If you take a look at VA deaths, which we saw here, you can see that basically this is a matrix where we have the columns named for rural and urban males and females. And we have the age brackets that are in the column, right? So we could say this is basically, I believe it's the death rate. Let me go ahead and look at, yeah, death rates per 1,000 in Virginia in 1940. So this is for the state of Virginia, the death rates for each of these age categories and for males and females that are rural versus urban, okay? So number 2 here says subset this matrix for only male deaths. Well, we can do that by simply calling the names. So here I say VA deaths, bracket, and I want to get all the rows, and then I just specify the names that are relevant to the males to get. And now I see in return, I get both the male columns and I get all of the rows. Now number 3 says subset for male death rates over the age of 60. So now what I want to do is I again subset VA deaths for those columns of interest. But now I say I want to get columns 3 through 5. And columns, or excuse me, rows 3 through 5 are associated with all those rows that are age 60 or above. And so this illustrates you can actually index in a couple of ways. If the rows or columns are named, we can index with the names. If they are not named, or if you just want to index by the row location, you can do that as well with the numeric representations. And the last thing said, calculate averages for each column and row. And so I could do the average, get the column means, which I get here, and I can get the row means, which is what I do here. All right, so let's talk about data frames now. Data frames are the most common data structure that you're going to work with within R. Here we see a data frame. Now this data frame is actually provided by the ggplot package, and we'll learn all about the ggplot package in a later module. But we can see this is what a data frame looks like within R. Right? We can see within here we have different columns, right? Manufacturer, model, displacement, year, and so on. And these can be represented by different data types. Here we have character values. Here we have character values. Here we have double floating points. Here we have integer values, right? So we can have all different types of data within a data frame. The main thing is the data within a column needs to be consistent, right? They need to be all characters or all integers. But across the columns, they can be different. So this is very synonymous to like spreadsheet style data that you may work with in Excel. Now, the one thing to realize here is that all the columns must be of equal length. And we're going to notice there's this thing called a tibble, right? So here it says tibble up here. Now, we'll talk a little bit about a tibble later on, but for right now, just realize it's a slightly modified data frame. It's still a data frame. It just has a couple of benefits, such as printing out a little bit more nicely than a data frame would print out within R. All right, common applications, holding imported data. So anytime we import, vast majority of our data, it's going to be imported as a data frame. Nearly all the exploratory data analysis we're going to be doing will be on a data frame. And when we do a lot of machine learning activities, the data we supply into and get out of our models will often be in a data frame form. How do we do some indexing? Well, actually, a lot of the data wrangling manipulation that we're going to do on data frames is going to be provided by a lot of dplyr functionality. So dplyr is a package There's some other packages within that tidyverse ecosystem that makes it very easy to work with data frames. But we can still do some basic indexing of data frames, just like we did with matrices and vectors. And again, we can do that with the bracket notation. So for example, in our MPG data, we can go ahead and we can get the first 10 rows and then these 3 columns of interest. So this is very much like what we saw with vectors, where when we index with brackets on a data frame, we have to specify the rows of interest and the columns of interest. Now, one thing to point out is there's 3 main ways that we can extract stuff out of a data frame. So most of the time we're trying to extract out a column. So all the values in a given column. And we can do that in 3 different ways. We can use a single bracket, we can use double brackets, or we can use this $ and then specifying the column of interest. The main thing is what we call preserving the data structure versus simplifying the data structure. When we do it with a single bracket notation, the output will be a single column, but it'll still be a data frame. However, if we do it with double brackets here, or with the $, the output will actually be simplified to a vector. Okay, that's kind of a key difference to keep in mind. Do you want to index but preserve it as a data frame, or simplify the output as a vector? All right, so go ahead, pause the video, and I want you to kind of work through this your turn exercise, which focuses on the mtcars data set. So mtcars is a built-in data set, which we see here, that has a bunch of different information such as the miles per gallon, cylinder, displacement, horsepower, and so on for these different vehicles. All right, so hopefully you got through that. The first question says, apply the head and summary functions of mtcars. What do these return? The head function is useful if we just want to look at the first so many rows. Right? So we can do head mtcars. By default, it gives us the first 6 rows. We could always say, hey, give me the first 10 rows, and I can get that. Now the summary function actually provides us summary statistics for each of the variables within our data frame. Right, so if I do summary mtcars, I see for each column, it gives me basically the numeric kind of distribution, the min, the median, the mean, and the max, and so on for those columns. Right, so that's a quick way to see some simple summary statistics for each column. Number 3 says index for just the MPG column at mtcars using 3 different approaches: single brackets, double brackets, and the $. How do the results differ? So if you went through this, you would see that single brackets returns a data frame with just the MPG column, whereas the other 2 approaches will return the vector, or the output as a vector. And then the last thing was use one of the methods in number 3 to save the MPG column as a vector. Now compute the mean of this vector. So recall that when we compute the mean, we typically compute a mean on either a matrix or a vector. So what we want to do is extract mtcars out as a vector, right? And so we can do that with the $. And then if I just wrap that with mean, I will get the mean of all those values in that column. All right, last one. Let's take a look at lists quick. Now, lists are the most flexible data type. We say that there's one dimension, but basically it's one-dimensional in that it can hold just about anything you provide it. It could hold a single numeric value. It could hold a matrix. It could hold a data frame. It could hold even another list, right? So a list allows us to combine many different other data values or data structures all within one single list structure, right? So it's kind of synonymous to a shopping cart where you just put a bunch of different packages inside it, but the shopping cart can pretty much hold all of them. Now, what's the application? Well, we won't build a lot of lists, but a lot of times the results that we get when we do like some statistical modeling activity actually gets supplied as a list. So it's important to understand how do we do indexing of a list so we can get things out of a list when we get a list supplied as a result from some analysis. For example, the same thing exists where when we index a list, we can either preserve the output as a list or we can simplify it to whatever that data structure is. So for example, let's go back here. We have this list, and here we have item 1 is a vector, item 2 is a matrix, and item 3 is a data frame. So let's go ahead. And if we were to go ahead and extract the first item 1, which was that vector, right, with single brackets, then what we see is that output is actually a list in itself. Okay? Now, if we wanted to get the vector out of that list and have that output as a vector, we would want to either use double brackets or this $sign to extract it. Okay. All right. So a classic result will be when we start getting to modeling activities. Okay. I don't expect you to understand what's going on with this code. Just realize that what we're doing here is we're building a linear regression model. Now the output of this model is a list that contains 12 different items. It contains the coefficients, the residuals, and a bunch of other stuff. So if you wanted to extract the residuals out of this list, then you could do so by calling the list, which is called model, and then doing double brackets residuals, and then we actually, let's say we want to get the first 10 of those residuals, right? So we pull the, let me run this code on my end so maybe you can kind of see this here. All right. So we have model, which is a list in itself, structure model, right? So this is a list, it's got a bunch of stuff, and this looks a little bit hairy. Don't worry about that. So now let's say I wanted to get the residuals out of my list. I could do residuals, and that will supply my residuals as a vector. Now, if I didn't use double brackets and I only use single brackets, remember, single brackets will preserve the output as a list. So now we get, it looks very similar, except we see this little $sign residuals. That means this is still a list as an output. So say we wanted to get the residuals out, but then we wanted to get the first 10, right? So now we would index those residuals like that, but now we can index that output for the first 10. Okay, and that'll get the first 10 residuals. Now here's the thing. This may seem a little bit convoluted because you haven't worked a lot with lists. The main thing here is to realize that lists are very complicated structures sometimes because they embed many different things in there. And lots of times we have to combine several indexing operations to get what we want out of that list. And we'll get plenty of practice on doing that throughout this course. All right, main takeaway here. First of all, get familiar with vectors and data frames. Those are going to be the two main data types that we're going to be working with a lot. The next one will probably be lists because we will start to do some modeling activities, and a lot of those results will be provided in a list. And then I would say matrices and arrays are those kind of data structures that you may eventually run into a little bit, but they're not used a ton. But it's definitely worth understanding how to work with them. And we can pretty much do indexing across any of these structures using the bracket notation. Then also for like data frames and lists, we can always pull individual items out with a $sign as well. All right, so if you get any questions, first of all, take a look at the lesson reading. That'll go in a lot more detail on this kind of stuff and give you some code to practice writing. And if you still have questions, hit up the discussion board in Canvas.